virtually impossible to know how much heat an object contains, but when heat moves, we can figure out how much heat moved and in which direction. Calorimetry is the precise measurement of heat flow into or out of a system for chemical and physical processes. To do calorimetry, we need a piece of equipment called a calorimeter. This is a calorimeter. It can be made of really expensive materials and be incredibly efficient at insulation. Or it can be a styrofoam cup and do a darn good job of insulation as well. All you need to do this at home is 2 stacked styrofoam cups, a thermometer, a lid, a stirrer, and a known volume of water. Let's say you have all of this ready to go, and you've read the initial temperature of water. Then you'll take a hot piece of copper, maybe let's say at 90 degrees, and drop it into the calorimeter. As you stir, you'll see the temperature rise. Eventually it will stop rising when it's at equilibrium, meaning the water and the copper metal are at the same temperature. The heat given off by the metal is absorbed by the surroundings, which include the water, stirrer, cup, and even the thermometer itself. The majority of the heat will be transferred to the water, and for the sake of simplicity, we'll do calculations assuming that all of the heat is actually transferred to the water. We'll try a calculation to figure out the heat transfer at the end of this video. Often you'll come across the word enthalpy instead of the word heat. If pressure is constant, we can use change in enthalpy essentially interchangeably with the word heat. Enthalpy truly accounts for all total heat in the system, but if you measure the change in the enthalpy, it's the same as the heat transfer. The amount of heat lost or gained by the system will be equal to the amount of heat gained or lost by the surroundings. So the equation for delta H is this. Heat of the system is equal to the negative heat of the surroundings, which is negative mass times specific heat capacity times the change in temperature. If delta H is negative, it's exothermic. If it's positive, it's endothermic. Just like heat, Q of the system. Remember, delta means change, so when we find the change in temperature, always calculate it by taking the final temperature minus the initial temperature. In a thermochemical reaction, you can show heat as a product or as a reactant. If the product is heat, then it's an exothermic reaction. Heat is being released. If the reactant is heat, then it's endothermic, and heat is being absorbed. The heat of a reaction is the enthalpy change for a chemical reaction. It's important to show the state of matter for each reactant and product when showing the heat of reaction, which in this case is 65.2 kilojoules. The state of matter is important because it can actually make a difference in the reaction. Here's the decomposition of water, starting with liquid water, and again, starting with water vapor. The resulting enthalpies have a difference of 44 kilojoules of energy. This is why the state of matter needs to be explicitly marked in the chemical reaction. There is a difference. You will also see enthalpy as heat of combustion, which is the heat of reaction for the complete burning of 1 mole of a substance. The heat of combustion will always be a negative number, because combustion is an exothermic process, so heat is always released. Now let's try a sample calorimetry calculation. An unknown piece of metal weighing 50 grams at 90 degrees Celsius is dropped into a calorimeter that contains 200 grams of 25-degree water. The final temperature of the water is 28.3 degrees Celsius. What is the specific heat capacity of the metal? First, we'll calculate the amount of heat absorbed by the water, because we have all the information we need. 200 grams times the specific heat of water, which we can just look up, times the final minus initial temp, our units of grams and Celsius will cancel, and we get 2,760 joules. Because the water could only absorb heat that was released by the metal, we can assume the same amount of heat was released as was absorbed. So now we can solve for the specific heat capacity of the unknown metal. So here's our equation. But we actually want to solve for specific heat capacity. To isolate it, we'll need to divide both sides by m and delta T. This makes the mass and delta T on the right side of the equation equal to 1, and we'll get it cleaned up and have this nice equation. Now we can plug in the data and calculate, and we'll get 0.9 joules per gram degree Celsius, which is the specific heat capacity of aluminum.
In this video, we are going to look at exothermic and endothermic reactions. So what are they? How are they different? What about their energy levels? In the next couple of minutes, you'll know everything you need to get started. An exothermic reaction gives off energy to the surroundings, like this fire giving off heat, whereas an endothermic reaction takes in energy from its surroundings, like this poor melting snowman taking in the heat. Just remember, exo means external, so giving out, and endo means internal, so taking in. Let's start by having a quick look. Because exothermic reactions transfer energy to the surroundings, and this energy is usually heat energy, they cause the surroundings to heat up, just like a bonfire, keeping everyone warm. Other examples of exothermic reactions are the neutralization reactions between acids and alkalis, the reactions between water and calcium oxide, and respiration. It is easy to detect exothermic reactions. Just get your thermometer and see if the temperature increases. Watch the hydrochloric acid and sodium hydroxide solution being mixed and see how the thermometer increases. Most chemical reactions are exothermic because heat is given out. Physical processes can also be endothermic or exothermic. When something freezes, it goes from liquid to solid. Bonds need to be made for this to happen, and to make bonds you need to do some work. Thus energy is given out and freezing is exothermic. Similarly, when condensation happens, because the gas is going to liquid, again bonds need to be made, and so energy is given out. So freezing and condensation are both exothermic. Because in exothermic reactions, energy is given out to the surroundings. This means that energy of the reactants is higher, and the energy of the products, hence the energy curve for the exothermic reactions, will look like this. Now let's have a look at endothermic reactions. These are less common. Remember that endothermic reactions take in energy from the surroundings. Again, as with exothermic reactions, the energy being transferred is usually heat. So in endothermic reactions, the surroundings usually get colder. Again, we can detect endothermic reactions with a thermometer, because the temperature would get colder. Some examples of endothermic reactions are electrolysis, the reaction between sodium carbonate and ethanoic acid, and photosynthesis. Endothermic reactions can also be seen in physical processes. When something melts, it goes from a solid to a liquid. For this to happen, bonds need to be broken. And to break bonds, energy needs to be put in, like our melting snowman. Boiling is also endothermic because energy needs to be put in to break the bonds for the liquid to turn to gas. Because in endothermic reactions energy is added to the reaction, the energy of the products is higher than the energy of the reactants. And so the energy curve looks like this. So there you have exothermic and endothermic reactions. All you need to remember is that exothermic reactions give out energy and endothermic reactions take in energy. Both can be detected with a thermometer. In exothermic reactions, the surroundings get hotter, and in endothermic reactions, the surroundings get colder. Exothermic reactions start with more energy and end with less, while endothermic reactions start with less energy and end with more. Freezing and condensation are exothermic because bonds need to be made, which gives out energy. Melting and boiling are endothermic because bonds are broken, which requires additional energy. Think of the snowman again. And finally, exothermic reactions are more common.
The lattice energy is the energy required to completely separate a mole of a solid ionic compound into its gaseous atoms. The lattice energy is difficult to determine directly from experiment. However, it can be calculated from other quantities that are known by taking advantage of a thermochemical cycle called the born-haber cycle. Let's begin with a mole of solid sodium and half a mole of molecular chlorine gas. This gives us 1 mole each of sodium and chlorine atoms. Now we imagine that the sodium is sublimed to form a mole of gaseous sodium atoms. We also imagine the dissociation of the chlorine-chlorine bond in Cl2 to form a mole of gaseous chlorine atoms. The first process corresponds to the heat of sublimation of sodium, the second to the dissociation energy of molecular chlorine. Next, let us ionize the sodium atoms to form separated sodium ions and electrons. The energy of this process corresponds to the ionization energy of sodium. Addition of an electron to the chlorine atom corresponds to the electron affinity of chlorine. The lattice energy of sodium chloride is the negative of the energy released when a mole of solid sodium chloride is formed from the separated ions. We have experimental values for the 5 steps in the indirect path for formation of solid sodium chloride from the elements in their standard states. We can calculate the lattice energy by taking advantage of Hess's law, which states that the energy change in a process is the sum of the energy changes for the several steps that may make up a pathway for the process. The lattice energy calculated in this manner is 788 kilojoules per mole.